Okay, so we're sharing the screen. Okay, so if you remember last time we were doing the GPT, right? So we were on video two, if you will, of that. We're going to continue. To go over that technique, the algorithm. So maybe today we'll finish. We'll go over all the concepts, and you should understand hopefully how a GPT works. Keep in mind that covers a lot of things actually related to PyTorch and how to build, neural networks. So these are pretty complex neural nets. I do have some. I'll start today. Actually, we're going to talk about one of the most important parts of the GPT, which is the attention mechanism. So I will talk to you about that. I actually have a separate Jupyter, if you remember from those 109 problems. So we'll go over that first. So outside of the context of the GPT, we're going to look at it and then we're going to see how it fits into the GPT. Okay, so that's basically the idea. So I'm going to go ahead here and start my. So let me take a look. I should have ITS 520 2024 fall. So I believe this is the one that we were using. GPTs, right? And I had a Jupyter notebook, the HuckFin one. We have the HuckFin data, right? So I'll continue going through this one, and you'll see this video as part 3. All right, once we finish these GPTs, the next topic obviously is going to be image processing and all those ideas. So let's go ahead and get started. So I'm going to open up the Conda prompt. And then while this is going on, don't forget you have a homework assignment due, I believe. It's due tonight. I extended the deadline, but it'll stay open, I think, until Sunday or something like that. All right, so make sure you submit that homework. Hopefully you found it easy, I assume. Okay, and then once we finish this, you will be getting a second assignment. All right, so let's go ahead here. I'm going to navigate into my desktop. There. ITS 520 D24. Okay. DIR. All right, so GPTs basically GPTs. All right. So here we are. As I said, our goal is to continue. You need to understand this algorithm really well, okay? So you can expect the second exam will pretty much just be this. Okay, I will take different parts of it and the question, about attention and everything. So definitely stop me, right, if you're not understanding something. But that my goal, if you understand a GPT, you can consider yourself capable of building any neural network, architecture, right? Because this is such a complex one. So today we're definitely going to go over the complex abstractions of how we built it. I think the last time we were just looking at the instantiation class, and then from there we had to build the actual architecture, right? So we're going to pick up there today. Okay, so I have this. So I'm going to check Conda environment list. Okay. Conda activate. And we were using probably ML 2024, I want to say. 538. $2024. Okay, so if you think about it, right, as what have we covered? You've covered 2 classical methods of machine learning. Do you remember which ones those were? They were linear regression and logistic regression, right? And then after that, we built multi-layer perceptrons and deep neural networks. Okay, and now basically you're doing a homework assignment, building neural networks. our topic currently is, a very complex neural network, which is the in transformers, just the GPT part, which is the decoder of the transformer. All right, so we had covered all of that. You can go over parts 1 and 2, those 2 videos. If you don't remember anything, I'm just going to pick up from where I left off. All right, so I've done this already. So now DIR, so it's that. So I should be able to do Jupyter Notebook. Browser. Actually, I'm just going to. Yes.
I was asking you, what are those cookies translate exhibits?
They're on the YouTube channel. I think I provided a link. It's they'll say GPT from scratch, maybe part 1 and 2. Yeah, I'll show you in a second. All right, so this open. I usually like record everything, right? So if you want, if you got everything from from the class, then that's great. You can go here, and then YouTube. So this is the YouTube channel. So I usually post all the videos here, right? And it's gonna be so this one describing a GPT from scratch with PyTorch part 2 and then part 1. Yeah, watch those, and I'm just gonna pick up from where we left off, and then we're gonna do part 3 basically today. And I think this could be the last one actually that we do. We should be able to wrap it up basically. So I'm going to do. I want to show you. So GitHub code is here, 2nd edition. All right, transformers, GPTs. Okay, so today we are going to cover these 3 Jupyter notebooks, NN linear. So I'm just going to show you basically what NN.linear is, which is that function that we've talked about, y equal wx plus b, right? So I'm going to do some math there with Jupyter notebooks that we're going to do the mapmol dot product. That's also called a projection. It's key concept in machine learning, transforming from one vector space to another vector space. Then I have this worked out, the attention mechanism just broken out into a separate thing. All right, so we're going to go through this one, and then we're going to look at the GPT itself. Does that make sense? So that's kind of, and hopefully some of these problems you've already practiced when you were doing your 109 problems that I gave you at the beginning of the semester, right? The examples. All right, so let's start with this one. This is my simple one. I like to start here with the idea of, I call it NN linear xw plus b mapmol, right? So I couldn't be more obvious there. All right, so I'm gonna just copy this code and we're gonna go through it. As you can see, it's a very simple example. So I'm going to go over here to this one. So I'm gonna create a new script. I don't want to modify my Huck Finn, so I'm just gonna do Python 3. Okay, there we go. I'm going to add a few cells here. Okay, I'm going to just rename this, NN linear. Okay. All right, so I said we use a lot in PyTorch the construct NN.linear. Right? You guys use this, and all you have to do is define some dimensions here. Right? All you do is that. But this is really just, it's the formula y equal wx plus b, right? That's the key thing in a neural network that's happening. And so we're just going to think about this idea a little bit today. And I do have my whiteboard, so we'll think of it in terms of something called a vector space, right? So what we're doing. But this is sometimes called a projection, right? And that's critical concept in machine learning. Something that if you command projections, you'll get a lot of insight of what's going on. All right, so the first example, I have it here. So we're just going to import torch, right? So I'm going to put a comment here. And I'm going to import torch. Okay, so I'll give it a minute there. Okay, so perfect. So I'm going to do the operations here. So what I like to do is just kind of print the shapes constantly, which is something that you won't see like in the GPT code. It's all like, not made so that you can print out what's happening from one line to the other. So I've kind of broken this up here in how it works. So the first thing I'm doing is I'm going to initialize an X, right? So basically what is it? It's iris data, for instance, just to keep a pretty clear concept, the iris data set. 150 samples, 4 features. So it's a matrix of 150 by 40. But so that basically is like a vector space, right? It lives in a space of 4 dimensions, and every sample in that space is a point. But the key thing with transformations is that you take the samples and you map them into bigger vector spaces, and you let the neural network figure out that mapping. That's kind of the idea through the neural network. And so that's what I want to kind of intuitively show you, right? Because the attention mechanism and all that stuff does these operations quite a bit. Does that make sense? All right, so here I'm going to do it. So imagine the data doesn't matter. Okay, the data doesn't matter because remember that you create architecture with random values. And then when you do the forward pass and the back propagation, given inputs and outputs, the neural network updates those weights basically. And so you end up with the right values that you want. So that's like the key things that are going on. Build the architecture and then give it data so it goes forward, backward, and in a loop, and eventually the weights get better and better at the prediction task. All right, so that's kind of what we're doing. So here, as I said, I like to start with iris 150 by 4. What I want to end up with is 150 by 6, which basically means that I'm mapping every single sample of those 150 iris flowers into a higher dimensional space, a vector space of 6 dimensions. And that's the whole trick in machine learning. And that's why it's called transformations, etc. The key thing, all this data is random. It would be optimized and the weights would be learned correctly. And it's almost like you're letting the neural network be smarter, think about things. I know that I have sepal length, sepal width, petal length, petal width. But you know what? I don't care about those exactly. I'm going to create 6 new features, and I don't really even know what those are. The neural network will figure it out. That's the beauty of it, right? You don't really need to know what they are, but it'll create these 6 things that are useful for it to do the prediction later on. All right, so let's do this operation. So I'm going to go ahead and so this is 150 by 40. So I could fit this into an nn.linear, but I'm actually going to do the map mole operation directly, right? And I've not included the bias just to keep it simple here, although the bias would be included. We'll include the bias a little bit later. All right, so I'm going to go ahead here and put in W. So notice this W is a shape that I need to know, right? This represents a matrix multiplication between X and W that will give you the next thing, right? So the Y basically. So remember, we are kind of nn.linear does Y or H1, which would be the hidden layer. So H1 given X, this is a matrix multiplication, W, and then there would be a bias, which we will add later on just to keep it more, make it more precise. But for now, I'm just ignoring that, right? So by doing this now, I've created this W 4 by 6. These shapes have to be specific because I'm going to do a specific matrix multiplication between these two, all right? So it's got to be these dimensions. So now I'm going to go ahead and do that. So I need to print the shape. So you can see I have a tensor now. 150, comma 4, and then 4, comma 6, which will have the weights. So now when I do the transformation, I'm just going to perform the operation here. So it's going to be, if you notice I'm doing torch mat mole. There's also an @ sign that is the same thing, but this is the matrix multiplication between X and W, and that produces Y or H, the next hidden layer. Key thing is you transform your data to the next layer, basically. So now if I print, see it's still 150, but now comma 6. I have somehow mapped those into a higher dimensional space. And that can be whatever I want it to be, right? Just by changing the 6 over here. But the key thing is you build this architecture, boom, it's like nicely done, random values, now start training. Does that make sense, guys? That's basically what the transformer is in the GPT. Any questions about that? All right, seems like it's clear. So now we're going to take it a step further, right? So this is like the very basic operation, the whole underlying operation of machine learning. This is one of the equations. Remember, there's the other equation. Once we've created this architecture, how do we learn those weights? That's going to be like the loss function. That's the objective that we're trying to reach, but that's not what I'm doing here. We're just building architecture. So now I'm just going to continue down here. So let's just say here, I'm going to look at the second Jupyter notebook that I have on my GitHub. It's this one. Linear algebra, attention, and ends, right? So now, GPTs are basically a whole bunch of these operations, right? A whole bunch of transformations. You've seen how we started with X. If hopefully go back to those videos, right? We took X and what did we do? We created the IDs, then the IDs we mapped into embeddings, and we also talked about the positional encoding, right? And we kind of got to that point where we had now our data as a tensor that was n by 40 by 512. Do you remember that? That's the one key thing that you need to remember, right? N is the number of batches, 40 is the sequence, and then 512 is the embedding that the neural network is going to learn. We've covered this, okay? Now, what needs to happen in there is that data needs to continue to be processed. But the GPT has one key like insight, or it's believed that that's like the power of it, and that's called the attention mechanism, the self-attention. All right, so that's what we're going to look at now. So it's got this idea of key queries and values, KQV. I'm going to stay away from that, and I'm just going to show you the mechanics of how it works, and you should see that it's pretty straightforward, okay? But the idea is that you have a sentence, the cat is sleeping, and you're going to have each of those words as a row and also as a column. The cat is sleeping, the cat is sleeping. So I do have an example of that. Okay, so if you go to the notes, by the way, hopefully you're reading the notes. So in here, I kind of have a graph. It's a pretty sophisticated graph I created for this. There it is, very sophisticated. All right, so anyway, so that's a sentence. The robbers broke into the bank and stole money. Okay, that's the sentence. And I have it on the rows and the columns. And the idea is that the attention mechanism is a matrix that is going to learn values so that it says, okay, when I'm talking about the robbers broke into the bank and stole money, bank and robbers, there's a specific meaning there, right? But there's another type of bank of the river. And that bank of the river should have a different embedding than this bank. Do you see that? And so that's what GPTs are, basically. As I think I've mentioned this, they're giant embedding machines, but they're embedding machines that look at context. So whenever they're because remember, we take the IDs, map them to these embeddings that are random, and then we train, right? But it should train that, when it sees robbers and bank, okay, those are somehow related. The meaning of that bank is a bank, an institution with money, right? And when we talk about bank of the river, that's a different embedding. So that's kind of what we're trying to achieve here, okay? So it pays attention, and this gives it obviously a lot of power, basically. And the way that it does that is through something called the attention mechanism, which is basically just a way of figuring out that there should be a weight, a strong weight, between robbers and bank, for instance, right? Like this value should be high. And that tells you, okay, robbers and bank, I know what we're talking about. We're not talking about Bank of the River. We're talking about robbers robbing a bank. And that provides a little bit more semantic understanding. Do you guys see that? So that's kind of the intuition of it. We want to create, so keep in mind that this is a N 40 by 40 matrix. Why 40? Because our sequences are of size 40. Now, this sentence is not of size 40, but then we still need to specify a fixed value, right? So we could have sentences that are of size 40, and for this type of sentence, we would just pad it. Does that make sense? So we ignore basically the padding, but because the buffers need to be a specific size, we've chosen 40. Therefore, our matrix will be 40 by 40, and we will see that. Does that make sense? Again, we're just going to do more complex operations than the one that I just did, that transformation. Okay, so we're just going to do some of those. All right, and then we're going to get into the GPT itself, and so hopefully it'll be clear in your mind how that works. Okay. All right, so I'm going to go ahead and look at that Jupyter notebook. So that Jupyter notebook is this one here. As you can see, I have the whole attention mechanism here from beginning to end. And I'm only going to think about this mechanically and how it works, right? Our goal is to create a matrix that is 40 by 40, all right? That compares the sentence to the sentence. Do you guys see that? And you should agree that the sentence is the sequence of IDs. All right, so I'm going to go ahead and just copy some of these libraries. This one in particular, so that I can print the shapes as we go along. So this should be the attention. This is just going to be useful for something called a softmax. We'll take a look at that. It's like a trick that they use for this operation. All right, so attention converts. So this is the first step, right? And let's think about this mechanically, right? And how it works. So attention will have three elements, K, Q, and V. So the attention will convert X into K, Q, and V. Okay, so how does it do it? Just the operation I just did, a transformation, right? So why do we do that? So X, think of X as the sentence, right? The cat is sleeping. So then we would do the cat is sleeping to the cat is sleeping. But the thing is, we don't directly map the cat is sleeping to the cat is sleeping. Instead, we take the cat is sleeping times some weights to produce K. And then the cat is sleeping times some weights to produce Q. And then we're going to compare K and Q. Do you see that? So instead of comparing the X to the X, we compare the K to the Q, but the K and the Q are derived from the X. It's just a way of I would describe it in a simple way as just giving the neural network one more layer to think about this thing. Don't just take the X directly, transform it into something that's more useful, and then compare it. You see that? It just gives, it gives more freedom to the neural net. So here, attention convert, and this is the hardest part, by the way, of the GPT. Everything else is just like coding with object-oriented programming. This is the hardest part. So if you understand this part, you understand what ChatGPT does. ChatGPT is just this with more layers, bigger embeddings. I heard Llama 3. I'm using 512. Llama 3 is 12,000 in embedding size. And this is only 512. All right, so attention converts X into K, Q, and V and performs the attention mechanism by the matrix multiplication between K and Q. So I'm going to do that. Okay. Okay, all right, so I'm going to go here. All right, so I'm going to use, to keep consistency with the actual GPT from scratch code, I'm using certain things. Like if you notice, this should be familiar to you, right? This you already know how to obtain, N, 40, 512. This is the original IDs that have been mapped to the embeddings. Probably the positional encoding would be there. All that is already there. I'm using a batch of 32, okay? And that's basically where we're at, okay? So this idea here, if you remember, just to look at the big picture of the neural net, the GPT, we are basically at this stage, right? And we're going into all these blocks, and each one of these blocks will have attention layers. And then otherwise, it's just very simple feed forward networks, etc. All right, so now I'm going to go over here, So I have my tensor X. That's the data. The cat is sleeping. The robbers are robbing the bank. Now I'm going to take this X and just transform it into this K and this Q. And you'll see how, hopefully that should be pretty clear. So let me do that. You can see I have my Jupyter here. So this is going to be Q, right? So I'm just going to create a W. So I'm going to say Q. Oops, I'm gonna add some more. I'm going to create a W, right? Why am I creating a W? Because once again, I'm going to do Y equal W times X plus B. When we look at this in the code, this will actually just be nn.linear. Okay, so that's what it's going to be. But here I'm doing like the whole operation. All right, so create the W. There it is. 32, 5, 12, 64. Why 64? This 64 is like my previous example where I did 4 comma 6. I was trying to project a vector space from 154 to a vector space of 156. Exactly. Here then, I'm trying to project a vector space of 512 to a vector space of 64. Effectively, I'm compressing it. Do you see that I'm compressing it? This will make sense later. This is necessary for what is called a multi-head attention. Like, imagine it's like a dragon with 8 heads. You see what I'm saying? So basically what we're going to do is we're going to calculate attention 8 times in parallel. So think of it as a dragon with 8 heads thinking about the problem 8 times in different ways. And then we're going to put it together to create a vector again. So why 64? Think about it. 8 heads. The original one is 512. What is 512 divided by 8? 64, right? So it should be 64. Do you see that? So we're just going to concatenate it, the 8 heads into one single head. Right? And that's it, right? Just so that we can think about it. Why did they do this? I mean, they invented this algorithm like this, and it works really well. I think now they have more heads. I mean, you can always add more heads, and it just depends on your computing power, basically. All right, so I've done the W, so hopefully that makes sense. This is the matrix for me to project, right? I'm going to project. So my 32, 45, 12, I'm going to project it to 32, 40 by 64. So projecting it into a smaller vector space. All right, so I'm going to go ahead and also I'm going to need the bias. Remember that the bias happens after the fact. So it happens you add it to the output, to the H layer. So I'm going to create a bias, sorry. So n 40 by 64, because once I project to n by 40 by 64, I just add that to it. Okay, so I'm going to go ahead and do that. Boom. All right, so now this part is to just perform the matrix multiplication. There we go. So I'm going to perform a torch matmul. You can also use the @ sign. Traditionally, matmul was the name of this function, so I just like to continue the tradition. So it's x times wq, but it is a projection from n by 40 by 512 to n by 40 by 64. All right, so I'm going to go ahead and do that. And you can see, or sorry, yeah, n is 32. So 32 by 40 by 64. I have projected it now. Okay. Any questions about that? Okay, great. So that's done. I'm going to add the bias, and just to show that this is exactly what NN linear would do, you can even say bias equal false, and then it doesn't do it. And then now, boom, 32 comma 40 comma 64. So you've taken, remember that X, the robbers are robbing the bank and something, something. And now you've mapped that, which was 32 by 40 by 512 to 32 by 40 by 64. That's one of your values, right? Now you just repeat the same process, but for K. And remember, because the idea is to take those two sentences and create this attention mechanism that should be 40 by 40. So now I'm going to go ahead and create K, as you can see. Similar process. I'm going to use the same X. It's literally the same thing, with the one thing that the weights should be different, right? It should have its own set of weights. So this one is K. I'm going to do run here. Okay, so now I'm creating WK, another weight matrix, n by 512 by 64, similar to 4 comma 6, just so I can project it to this lower dimensional space. There we go. I have that. Then I'm going to do the same for the bias, exactly the same thing. That's done. And then I just add them up. Oh, I need to perform the matrix multiplication, sorry. I'm going to do the matrix multiplication. So remember, the X times WK, its own set of weights, and boom, it's projected to 64 as well. Does that make sense, guys? All right. So now I add the bias. All right. Yeah, please.
Can you describe how this batched multiplication works? I mean, we know of matrix multiplications in, I mean, if they have rows and columns, right now they are 3 dimensions. So how does it?
The last one. It's the last one. So you need to think of it as like I did here 40 by 64. So let's see, 512 by 64. So yeah, it would be, let me do here in the original one. So 512, this is 40 by 512, right? So 40 by 512.
By 40 by 512.
Right, but you can ignore the n here. So because it's a broadcasting operation. So if you think 40 by 512, and this is 512 by 64, so it should be 512 to 512, 512 to 512, and it creates 64. So the 512 times the 512, and you do it 64 times.
But which one, like for the first 10 will be multiplied? I mean, where does the n come in? Because we are going to have n 40 by 50 512 matrices.
Yeah.
Then do we multiply the first one with the first one, then second?
So I would so I would say it's almost like you can ignore the n. The way that I think about this is 40 by 512, because every token needs to be mapped into it, right? So and 512 to 64. So I would do 512 to 512, and that gives me that 164.
Yes.
So, but there's a broadcasting operation here that it does it by itself.
But I'm just wondering, like, what
Yeah.
does this mean then? I mean, we can look at it as like we have n 40 by 512 matrices. Then can we think of it that
N is the batch. So remember that n should be independent, first of all. Like
Right.
N1 and N3, there really should be no cross anything. So think of just one.
Yeah, but when we are multiplying, like I
Mhm.
think you multiply x with WQ, right?
I multiply the WQ times the X, yes.
Yeah. So in that case,
Mhm.
the n should have some sort of, impact, right? I mean, we are multiplying those two.
Maybe. I mean, it produces the tensor that I want.
But there are n of those.
There are, yes, but the neural network will figure it out. You know what I mean? Like right now, the values are random.
Yeah.
So all that you're trying to do is like map this to another tensor. Do you see what I'm saying? So like this is n by 40 by 512, right, initially. And then it becomes n by 40 by 64.
Yeah.
So there's this tensor here and this tensor here. And really, you just need like the mechanics of it, because eventually you're going to concatenate those 8 tensors to create one that is n by 40 by 512. So it's like a clever way of doing it. You almost only care, this is the input, this is the output. Once you built that architecture, you give it the GPT inputs and outputs. And it's gonna, and because these are matrix multiplications, these are like network weights. So that's what gets adjusted. Do you see what I'm saying? So you just create it may not be the exact linear algebra operation, but it's the one that works for this problem. Do you see what I'm saying? Yeah. So, I mean, it works. Like you can see, literally, I get what I want by doing this matrix multiplication. Yeah. But don't think, so I guess I could say it like this. Don't think about it with meaning initially. Think about it mechanically from going from one tensor to the other. And then because it's a network multiplication, it's weights in a network. And that's the thing that gets optimized. Yeah. All right. So we obtain the Q, right? So that's what we have here. So we have the K and the Q. So now we should have two things. Let's see, K. I added the bias. So now I have 32 by 40 by 64. It has been transformed, hence the name transformers. Okay, so what do I have? 32 by 40 by 64, but really 32 is the batch, 40 is the sequence. Remember, 40 is the sequence. So 40 is the cat is sleeping or the robbers are going to rob the bank. And now what you need to do is you need to compare the K and the Q, which is like saying the robbers are robbing the bank and the robbers are robbing the bank, right? So we perform now a matrix multiplication between these things. And remember, we're going to do this 8 times so that at the end we concatenate these tensors into a final tensor. All right, so I'm going to go ahead and do that here. So you can see the attention mechanism part. Okay, it's going to be this one. Like that, right? So we want to obtain that matrix basically, which if you think about it, will look a lot like my matrix over there. And we are comparing X to X, but through K and Q, basically. All right, so that's what I'm going to do now. And if you notice, that's basically this operation over here. So it's a matrix multiplication matmul between the Q and the K with the corresponding transpose operation that needs to happen for the key aspect. Again, don't think about it as the intuition of what we're getting here, but instead of obtaining the goal of 32 by 40 by 40, which in essence is equivalent as you looking at robber and bank, you know, and comparing the different terms, the IDs. Except remember, you don't compare the IDs, you compare the embeddings themselves. Do you guys see that? This is the cleverness of GPTs. This is the whole attention mechanism. And that's it. You've done it. At this point, I have 32 40 by 40. Remember, the values here are still random, but that's when we start doing the training, the values get updated, and then it just so happens that robbers and bank should be a weight that's pretty strong. That's the basic idea. Got it? That's it. Like that's literally it. You'll see this in my GPT code. It's the same with the only difference that I'll be using nn.linear instead of the way that I did it here. All right, so now that I've done this part, the next step is there is a softmax thing. We'll see that in the code, but now I'm just going to see where the V comes in. But I can tell you right now, what does the V do? Well, we have a matrix that is 32 by 40 by 40. That's the attention mechanism. And once we have those attentions, we still need to convert it back to 32 by 40 by 64. We need to come back to that tensor operation, right? That's the mechanics of it. So I'm going to, once again, for V, I'm going to create the W and the B like that. So, oh, and I should say this one is V. This is the letter V. So that's the QKV that you see. in the paper. All right, perfect. So now I'm creating WV that's the same n by 512 by 64. I'm going to do that projection. So there it is. Then I'm going to take the bias for this one. Just like that. And then I should be able to perform, in this case, the map mole between X and these. So once again, I take the original X, which has the data, right? The IDs, the embedded IDs, and now I multiply times WV to create a tensor that is 32 by 40 by 64. Makes sense? That's the mechanism of attention there. And it just puts everything in the way that it's supposed to be for the neural network to be able to actually pay attention to the terms. So now I'm going to do that. So I have my BV. I did the multiplication. Yeah, I initialized. So I should be, when I run this one, it's 32 by 40 by 64. Okay, that's my BV term. So now what I want to do is, if you notice, I'm just going to take. So now I perform yet another map mole between the attention scores. So the attention scores was the thing that's the product of K and Q, and that had a size of 32 by 40 by 40. But I want to project it back to the thing that allows me to build a consistent tensor. So kind of like the design goal, I would say, with the GPT is always have n by 40 by 512 go in, n by 40 by 512 come out. N by 40 by 512 go in, n by 40 by 512 come out. They're keeping that consistency. So here I'm going to do attention scores times V, and the shape is 32 by 40 by 64. Do you see that? How clever that is? Does that make sense, guys? That's it. You got everything else. There's some like nice things going on, but there's a normalization that I didn't do and little things like that. But you'll see in the actual GPT code, it's very similar. All right, so now that I have my 32 by 40 by 64, what am I going to do? Now comes the concatenation of the 8-headed monster, right? Because I did 8 attention heads, each of 64. So this it literally is, you do it in parallel to take advantage of the GPU. It's like, you know, this is something that totally can be done in parallel, right? If you have 64 heads, each could run in like its own thread of the GPU or something like that in parallel, right? And then you just put them together. So here I've just made a very simple example and then I'll relate it to the GPT code. So let's go ahead here. So remember that out is one 32 by 40 by 64 tensor, right? That's what it is. So now, if you notice, I'm going to use the list comprehension here. All right, so list head, and basically what am I doing for I in range 8? I'm basically creating a list with 8 of these tensors. Obviously, in my example here, I'm using the same tensor 8 times. So that's not how the GPT works exactly, but it's a simplified version of it, right? So here in the actual GPT, these would be different. Each of these would have its own set of weights, because that's the whole point. It's like if I give a problem to all of you in this room, right? You get the same problem, but you'll think about it differently. Then you get together and you give me the answer. That's kind of like a design goal there. So I'm going to hit list, right? So I got my list head here of 8 heads. Right? You can see I have data there for the 8 things that I want. So now what I'm going to do is I'm going to just like print the shapes. So here I'm just going to print the shapes in the list. And you can see they're all 32 by 40 by 64. This is pretty much what the multi-head attention class will do for us. Only, as I said, they would be each of them would have its own set of weights because they've thought about the problem differently. So now these 8 need to be concatenated. Remember, this is the architecture in the original Vaswani paper. So I'm going to concatenate them, and they should result in a tensor, once again, that is 32 by 40 by 512. Effectively, tensor goes in, tensor goes out, right? And just keep in mind, the weights, as I said, are random. They need to be learned later. Okay, so now I'm going to go ahead, do that here. It's a simple concatenation operation of tensors on the last dimension. So torch cat here. Boom. See that? That's it. This is the magic of transformers, basically. Like in essence, that you implement the attention layer, and now we've got 32 by 40 by 512. Literally the thing that went in to all the heads, you know. Where's the X? All the heads, n by 40 by 512, n by 40 by 512, which is n is 32. But it's a sequence of steps, right? And those weights, think about it. You have all these weights and they're like terrible. Give it an input, it predicts something, try some weights, bad result. Next time around, try another set of weights, goes in, better result. So it goes through that whole architecture. And eventually, when it starts to produce good results, it's got a good set of weights. Okay? All right, so I've done that part. So now I have my tensor, and that's what comes out of the multi-head attention. And then there's an additional projection that will happen. And that's just because, neural, we'll see this, like the feed forward, there's just a projection that happens additionally. So in this case, I create this new weight, W0, which is N8 by 64, that's 512. So I can just map it to 512 again. So it's another layer, basically like a feed forward layer. And I'm going to have a bias there. Perform a map mul. (32 by 40 by 512). I effectively created the same tensor, but remember, those new weights in W0 also need to be learned. So it's a further transformation, basically, and an opportunity for the network to just improve. And it's output 32 by 40 by 512. That's it. That's actually literally the whole attention mechanism. Does that make sense? Any questions? Yeah, please.
Isn't the softmax operation like integral?
There is a softmax operation. I do have that here. So this is kind of like the multiplication and like from tensor to tensor. But there's going to be a problem when you do the optimization. And what you do is you want to set these values to infinity so that when you do the optimization, they basically become 0, like you see that here. So that's the softmax operation that you're speaking of. So it's a thing so that when you're optimizing, you don't have a problem, basically. So we can see that here. All right, so let's take a look at that one. So the masking, right? So the masking is the other part that you're going to see in the GPT code. All right, so you're going to see this mask, which is kind of like this mask here. There we go. So it uses torch.trill, which takes torch.once. I'm only using 10 by 10 here, so it's easier to visualize, but imagine it's 40 by 40. Okay, so I run that. It's a torch tensor of 10 by 10, right? And torch trill like that. Okay, so it's kind of like this. If I do it here, it's almost like you see the robber broke in. So let's look at it like the robbers broke into, and that's as far as it can look. So it doesn't look at the, right? Or the robbers broke into the bank, but it doesn't know what follows after, right? So that's what the mask basically is for. So I've created this mask here. And the attention mechanism is this one as an example. Okay, so attention is also of 10 by 10. Okay. And so here then, we're going to use trill for masking. So we need to change it a little bit. So we're going to use this code. And what do we tell it? We tell it that the values that are 0 should have an inf in there instead of a 0 in the trill. Does that make sense? So this will be part of the code itself. You'll see that. Okay, so now, if I grab this one. See, these values, which were zeros before, are now infinities. And that's the thing that he was saying with the softmax. The softmax will make, when you're doing the softmax optimization, these values will become 0. So it's kind of a trick that is used. Right? So softmax makes negative infinities close to 0, basically. Right? So I'm going to do that here. All right, so I take size 10 attention, which is this size 10 attention on the last dimension. I'm going to run it through a softmax. Okay, 32 by 10 by 10 is the same thing. This one. Zeros. Do you see that? So that's, when we do the optimization, the softmax function will basically zero out those values. So kind of a way of ignoring them. All right, so, and you can see that's the same as this. Make sense? All right, so let's take a look now. So that's the whole Jupyter here. So this was me breaking it down into like the individual operations. What I'm going to do now is I'm going to go into the actual GPT code, kind of point out where everything is that we just did, and that here I was able to print out all the shapes individually. Obviously in the code, they won't be broken out, but they will be there. All right, so let's now click on this one. And now I'm going to click on the Jupyter notebook. All right. So this is the GPT. So I'm going to scroll down, right? So we've covered all of this. And we were here basically, the NN architecture. So we looked at the head section, right? We have a class called head. We have a class called forward. We have a class multi-head attention. So some of these things now, hopefully, will start to make more sense to you because you'll see the operations that I just did in here, okay? All of them. I have the block over here and the GPT model itself, which is where everything starts. So let's take a look at the GPT model itself, right? So in the constructor, we have the token embedding and we have the positional embedding table. We've already discussed these in the previous 2 videos, but I remember that we kind of stopped here. This was the last thing that we looked at. Make sense? All right, so first of all, you're going to create the blocks, right? So what are these blocks? We're going to create these 8 or 6 blocks. We're going to create these 6 blocks called a coder layer, each one having an attention layer, okay? So that's what we're doing. We're doing it in a very clever way. So in the past, we've always done this approach where we take X and it goes into the function to produce an X, and then that X becomes the input to the next one and produces an X, and so on, right? Like we're passing it in. There's another way of creating constructs in PyTorch, and that is this nice thing called NN sequential. Okay, so I have another example of NN sequential here that I'll show you. I like to use NN sequential and CNNs just because there's a lot of things going on in CNN, so it's more convenient to code like that. So if I go to deep learning algorithms, second edition, I have an example in CNNs here. All right, we'll cover this once we start processing images. You can see here in this architecture classifier CNN, I'm using the construct NN sequential. Do you guys see that? And the beauty with NN sequential is I don't have to do that whole thing of X goes into something to produce a thing, X, and that's the input to the next X. And you see what I'm saying? Instead, you just put in NN linear, and then NN linear, and then NN linear. And the assumption is the X is going to go in at the beginning and go through them all. That's another way of doing things. And so that's what I will be using in the GPT for convenience, basically. So basically, whatever NN linear or con2D or whatever I put in there, they're going to be in sequence. So think of it as equivalently as you putting in an X that produces an X that becomes the input to the next one, and so on. That's what you can think of it. So there's 2 ways of doing it. We'll do this example in a few weeks when we start CNNs and leading up to more things. All right, so now I'm going to go over here. Oh, here. So now that I've explained what NN sequential does, you can see that I have basically a list. And this list is similar to what I just did before, right? So before I had this list over here. Where did I have that? Yeah, here. See this list? For I in range 8, and I just created a list of 8 outs, right? So that's something similar that I'm doing, but I'm doing it in the context of NN sequential. So that the X will go into the first out, what comes out goes into the next out, and then what comes out goes into the, and so effectively I create 8 layers very efficiently with 1 line of code, right? So that's the beauty of this approach. So you can see that here. So I'm going to do the I in range n layer, there are 6 layers, but I'm creating a list of blocks where I'm instantiating each block so that in the end, I end up with a list of 6 instantiated blocks, basically. Block is, of course, another class that we're going to look at as defined. But this little line of code basically creates all 8 blocks in the network, and the X will just go through them. Got it? So N512, N by 40 by 512 goes in, N by 40 by 512 comes out, goes into the next block, and so on until the end. All right, so that basically is what's happening here. So hopefully this part should be making sense. So the analogy, as I said, is that it looks a little bit like this one. So you can see that then we're going to have something like this, and then we want to do a cat operation, which is what I just did, right? So we're going to take a look at that. So let's go ahead. So the next step then in this example of blocks is to look at the object block, which takes in n embedding, which should be 512, and n head, which is either the size of the head 64 or the number of heads. So we'll take a look at that. So block is this one over here. That's it. So this is the block. So block here then, so n head is the number of heads. So n embedding is 512 divided by 8 should give you 64. You see that? So then I get head size of 64. And now I pass that head size of 64 to an n heads, to the multi-head attention object or construct, okay? That's the thing that creates my 8 heads, my 8 attention heads, okay? First, I created 6 blocks. Each of those blocks has a multi-head attention. Each one of those multi-head attentions will have 8 blocks, or 8 attentions. So that's similar to this. These are my 8 heads, and I want to concatenate them to produce n by 40 by 512 once again. All right, so we're going to go over here. So this one takes in a multi-head that will produce SA. You can see that here. And these are layer normalizations. So they're just normalizing the output. So I take X, gets normalized. That X goes into SA. SA is the multi-head attention. You can see that there. So I begin the process of the 8 attention layers. What comes out of that is a n by 40 by 512, gets normalized, goes into a feed forward. A feed forward is just a normal neural net. Notice one thing, X plus this is called a residual. And this is really important. This simple thing is what solved what is something called a vanishing gradients problem. So there's a thing called vanishing gradients problem, which basically meant that as you made your neural networks deeper, if you think about it like, you know, these may have 1,000 layers or something like that. But what happens when you multiply weights that are very tiny? They start approaching 0. Like if you do 0.5 times 0.5, I think it's 0.25. And then 0.25 times 0.25 is an even smaller number. So as you keep doing that over many layers, the numbers will become 0 eventually. So unfortunately, your neural networks, this was a problem for a very long time. The neural network just wasn't learning, right? So residuals is one of the solutions because it's really the data originally plus a little bit of it. Okay, so that is happening here. This is just a GPT architecture. So this is actually really important here. But anyway, so the SA now is where we're going to focus. So the SA is the multi-head attention object. So then we have to go to the multi-head attention, and that's there, right? So the multi-head attention object, if you notice, is a module list where you're going to instantiate not the blocks as we did before, but the heads, right? For each block. So we're going to create 8 heads. So notice here, 4 I in range num heads, which are 8. Head, that's the head object with head size. Does that make sense? And this is definitely equivalent to this, my out idea again, same idea, only for the heads. So I will have a list of 8 heads, right, created in this module list. So we have to then look at it over here. So I create the 8 heads. So then at 4 H in self heads, each one gets us input X. Do you see how clever that is? So X is the data, right? Yes? So X is the data. This is equivalent to, in my example, this X over here at the very beginning. Remember the X became K, X became Q, K times Q became attention, attention times V gave you the final tensor. But initially it started with an X. And I said there are 8 heads there. So that's what I'm doing here. So you can see I have the head objects. Now I iterate through them and each one of them will get the X input. And then what is this one? Torch cat. So that at the end of the day, when everything is processed, I have the 8 heads and I just concatenate them. Each one will be a tensor of n by 40 by 64 after concatenating n by 40 by 512. That is the operation that I did here. So these are the 8 ones. And then I did the cat operation and boom, 32 by 40 by 512. Make sense? Okay. All right. So take a look. So I have the cat there. And then that out is going to be projected basically to another out. So a projection is just going to be n embedding by n embedding, similar to what I did. Just, you know, giving it a little bit more, I would say giving it another layer of weights to learn to give it more room, I suppose, to learn. Yeah, please.
I mean,
Yeah.
not too relevant, but is there any advantage of using an NN dot module list rather than just a simple list in this case?
These are some very technical things with programming, so you can try it.
Sure.
Like this is just a list, right? So you just want to try a normal list?
Yeah, a normal.
Well, so a normal list in Python versus an NN dot module list.
Yeah.
I mean, it might be an optimized list for this. Yeah. So you'd have to read the documentation for it. I don't like, I guess I see your point.
I mean, the computation is being handled sequentially rather than in parallel, right? We compute the first HX, then the second, then the third, then the fourth, right? Maybe it's optimizing for that and like.
It's how it's doing it behind the scenes, I don't know, but it's 8 heads in a list here. This is a normal Python list, right?
Yeah.
Up to this point. Then that goes into module list that creates the object n heads. Then we iterate through it and assign X to each individual one. So they're definitely not connected. How this is distributed out to the GPU to do the operation in parallel, I don't know. That's going to be handled by PyTorch. Yeah, so you just create this thing. You might assume that possibly module list helps in that parallelization. Yeah, you can think of it that way because it is part of the NN module list. So they created it for some reason, but I don't know the definition of it. Yeah. All right. So anyway, so good question. All right. So what do we have now is the heads, right? So they've been concatenated, but we probably want to dig into these HX ones. So they're heads, right? So that takes you to this. That's the head. And that's the attention layer, which is the thing that I just described, right? So I described this to you guys in this script. So I went from X, and I told you that X needed to be converted into K and Q. K and Q are multiplied to produce N by 40 by 40. Then N by 40 by 40 is multiplied times V to produce that N by 40 by 64. That's how it works. So remember, no weights yet, only pure operations to build a network. That's literally what this does. If you think about it, you have a neural network that's, and then data will go through it and backwards, and the weights are updated. Okay. So now, hopefully, we did this one. So let's take a look at this one in the code. All right. So this is the head. So notice here, key, query, and value are that K, Q, and V that I did. Notice that instead of writing out the function, I literally just used the nn.linear, but they're equivalent, right? So that's the whole idea. So n embedding is 512. Head size is 64, right? So you're mapping from 512 to 64. Exactly what I was doing over here. Does that make sense? And notice that I don't have a bias. Bias is set to false, but hey, if you want a bias, set it to true. Do you see? All right. So anyway, so you create the construct K, Q, and V. Notice the torch trill is literally what I did in the example, right? So torch ones, block size by block size, which is 40 by 40. We created this and it had zeros and ones. Then this register buffer is just so that this part of the network is not updated by the weights. So you call it trill and you assign it trill depth. So it's kind of like a mechanical thing of the buffer of the network. My understanding is you don't want this part to be updated during the optimization. And then you have a dropout. So now we've defined these objects. Now basically this part here, the forward section, is going to be what we did here. Okay. So that's like a new sequence. So it's 6:15. Let's take a 10-minute break and then until 6:25, and then I will pick up here to finish up the neural network. Does that make sense? All right. So again, I want to stop at a point before we start the attention mechanism because it might be involved. All right. So let's take a 10-minute break and let's come back at 6:25. So I'll end this video.